So I want you to notice some part of time, the velocity over here, you can see that it's almost zero. You could almost see that velocity profile. This one. And then it increases the speed and you can't really see much. So at some instance, you could actually see that there is a certain velocity profile in that way. Because this is a pipe, so the velocity that's nearest to the pipe over there, that will be almost zero. And the velocity that's right in the middle is where the highest velocity is. So what is happening on that plate? This is what is happening. This is the boundary layer that we saw before, and this is the velocity profile. And this is the leading edge of the plate. And somewhere down, further down, you will see that there's a transition that's going on. And this part over here is actually what we consider the laminar flow. Let me blow this up. So this part over here is your laminar flow. And there's a region that's called transition, where it transits from laminar flow into turbulent flow. And over here, everywhere else, you have turbulent flow. So last year I asked this question. How about over here? What is it that's over here? What do you think is over here? Is it no liquid? Right. If this were to be air that's coming in, these are all your ambient air. Right? All this is your ambient air. If this is water that's coming in, that's your free stream water out there. This is your velocity boundary layer. So in the turbulent region, you get to see this kind of profile. This profile is not a velocity directional profile, but it's an average velocity. It's an average velocity. This one is the actual velocity in that direction. But because over here you can see every point your turbulent effect starts to come in. So the average velocity, you're going to get this kind of profile. So this laminar boundary layer region, the flow is very ordered, it's laminar. And the boundary layer thickness increases as we go along this axis. So this is y-axis, and there is your x-axis. The velocity gradient decreases within that turbulent region. So over here, later on there will be another slide to show that difference. And this surface shear also decreases. Right. Now, what I want you to see is this region over here. This is what we call this viscous sublayer. And this is already in your turbulent region. And it's actually laminar flow that's going on here. A very, very small little region on the turbulent side. So if you were to look at it, this is actually a good region that we'll be using, even though it's turbulent. Why? So that's because if I were to want to encourage heat to get transferred away from the plate, my laminar flow is not my best flow to remove heat away. My turbulent flow is the one that's going to remove heat away. Why so? That's because I don't have to let the laminar flow to convect the heat away. But turbulent flow just kind of like dig away whatever heat is on the surface. So the one that's immediate to that layer, to that plate, that one is laminar flow. But then somewhere further out, you will see that all these are turbulent region, and they actually could remove heat away a lot more better. So in fact, turbulent flow is the flow that we look at when we want to have good heat transfer. Now there is an example of this turbine blade. So for the turbine blade, what happens is that the flow U infinity is going to come in, and you will develop the same thing because this then will be your leading edge. So the flow will go past your leading edge, and then initially it's going to be a laminar flow, and then slowly go into a turbulent flow. But because the profile of your turbulent of your turbine blade is arced so well that you have mostly laminar flow that's going on in there. Okay? So that's one way to make sure that you wouldn't have much losses in transferring the energy to your turbine blade. This is a sketch of the difference between the laminar and the turbulent flow, where the gradient of del U del Y at this position when Y is equal to 0, and this is where we call the laminar region. This one is turbulent, and there's also another gradient over here. So if I were to sketch a gradient, something like this, if I were to sketch a gradient for this, something like that. If you turn your head around, this gradient is actually lesser than this gradient. Alright, if you turn your head around, right. So this gradient here is actually lesser than this gradient. This gradient is steeper. So turbulent flow here is chaotic motion, high level of mixing, high level of velocity fluctuation. That's why you see that we take the average. Right? This one is average velocity, represented with an over bar at the top. And the velocity fluctuation in the turbulent boundary layer greatly enhances this heat transfer. So if you compare the H value for turbulent, it will be larger than the H value for laminar flow. That means your convection heat transfer coefficient is larger, and that's why it encourages heat to get flowed out a lot more easily or better. Feeling bored? Serious? I can try to make it more interesting to you. Have more mathematics in there. Okay, just a couple more slides, yeah? The next thing I want to share with you is this term that's called Reynolds number. Some of you have already heard about what Reynolds number is. In fact, Reynolds number is a number that we use to decide if this flow is laminar or turbulent. That's what Reynolds number is used for. How do we decide that? We can see over here that this region is mostly laminar and that region is mostly turbulent. There exists a critical X distance away from the leading edge, of which the Reynolds number, if it's less than certain value, then we call it a laminar flow. If that Reynolds number were to be greater than a certain value, then we call it turbulent flow. What is that number? That number is 5 times 10 to the power 5. Do you think there is units for Reynolds number? Reynolds number is a dimensionless number, so there's no unit. So 5 times 10 to the power 5, that is the number that tells you if the flow is in laminar or in turbulent. Because after this information, we're going to make use of that to do other calculations as well. So if Reynolds number is less than 5 times 10 to the power 5, that means it's in laminar region. If it's more than that, then it's in turbulent region. But this value 5 times 10 to the power 5 resides in your transition zone. So sometimes certain textbook would say, no, yeah, you can't really put a number to that because it's transition. So generally, if it's significantly or kind of like, you could see that it's 4 times 10 to the power 5, yeah, that one is in the laminar region. If it's exactly 5 times 10 to the power 5, it's somewhere in the laminar transition region, but we gotta put a number to that. Some textbook actually will give you a range to say that if it's lesser than this range, then it's in laminar flow. If it's more than this range, then it's in the turbulent flow. So that Reynolds number is given by this expression over here. And again, your exam data booklet, you gotta bring you that in. Over here, you could find your Reynolds number value. So kind of like you don't have to memorize that. So it's given to you over here. Rho ux over mu. So some of you say that, hey, it looks a little bit different over here. I have u infinity. So that u refers to your velocity, and in the case of free stream velocity, that's u infinity. If you're dealing with Reynolds number in a pipe, then it wouldn't be x. Reynolds number for a pipe system, you'll be using the diameter of the pipe, and in this case, that'll be rho u infinity d.
What's the x again? What's the x?
Diameter.
No, for not in pipe, right?
So xc over here refers to critical length. So your Reynolds number, as long as it's lesser than that Reynolds critical, when you substitute x critical into the Reynolds number, as long as it's less than 5 times 10 to the power 5, you say that the flow is laminar. You need to indicate this in the exam, right? That is less than that value, hence is laminar flow. Or if it's more than that value, hence is turbulent flow. So this part is important. I want to introduce you another number that's called Nusselt number. It's a German word. Some read this in English. Nusselt. Nusselt number. I want to make a comparison between the Newton's cooling law to your Fourier's law over here. Newton's cooling law says that Q is equal to HA Ts minus T infinity, where Ts is greater than T infinity. And Fourier's law says that it's K A del T del Y, depending on where T is transferring across. Is it y-axis or x-axis? So these two Q are equal to each other, so I can equate them. Ka del T del Y. So A and A, they are common, so they will cancel off. And I can express H equal to K del T del Y divided by Ts minus T infinity. So that's how this equation comes about. So the problem in most heat transfer experiments, most of the heat transfer problems requires us to find out what is the H value. So again, I was saying that your lab will allow you to have that opportunity. But we haven't talked about Nusselt number yet. The Nusselt number Nu is equal to H L over K. I know here writes KF, this F refers to fluid. So I'm just ignoring that. That's the thermal conductivity of the fluid. So H here refers to the convection heat transfer coefficient. And L here refers to the length of the plate. L here refers to the length of the plate when you consider where is that critical Reynolds number. If you are dealing with a pipe system, this would be H D divided by K, because for a pipe system, you deal with the diameter of the pipe. But for a plate system, you deal with the length of that plate. So generally, this L over here is what we call the characteristic length. So if it's a plate, then that length will be X. If it's a pipe, then that characteristic length will be diameter. So we call that characteristic length. Yeah, I can hear some whistling. I know we are bored. But just one last slide, isn't it? Yeah? How about that? One last slide. Okay. Actually, I come from an educational system where I'm not allowed to whistle. But no problem. Right? No problem. Yeah, not cool, yeah, these days. Whistling in class, I know. Okay, just one last slide. Now, a lot of times, please note that we'll be using Nusselt number in order to help us to calculate what is H value. And later on, there'll be some examples to show us how to do that. So a lot of times, this H value that leads us to calculate what is Nusselt number requires us to do some advanced computational effort. But in this module, it used to be that we have a MATLAB course, but that has been taken away. So we wouldn't be dealing with any computational stuff. In fact, your Nusselt number is actually a function of your Reynolds number and Prandtl number. What does that mean? Now please note that there's an error in this part over here. This should be Reynolds number. This U, I kind of don't like it to be calculated like a U because it's a bit confusing. This U is your velocity. Velocity that we have seen before is written in small letter U. But this symbol over here, that is mu. This symbol is what we call the kinematic viscosity. And kinematic viscosity, I kind of like use this penmanship. The penmanship depends on your penmanship how you write that mu. This is a symbol that's not V, but a Greek symbol that's called mu. Right? It's like mu, and it's mu. So that mu is actually equal to mu divided by density. So this one is your dynamic viscosity. And mu would have the units of meter squared per second. So if you could substitute that in there, Reynolds number is equal to U infinity x over mu over here, that is mu, and you bring the rho up there. That will give you back your Reynolds number. Okay, that we have seen before. So this is another expression for Reynolds number. So back to the part talking about Nusselt number is actually a function of Reynolds number and Prandtl number. But what is Prandtl number? Prandtl number is your kinematic viscosity divided by alpha, yet another new symbol. Alpha here refers to your thermal diffusivity. That means how much your heat can diffuse away. Thermal diffusivity. It's given by this formula. Alpha is equal to K divided by rho Cp. So Cp over here is your specific heat capacity at constant pressure. Right. So if you are again wondering, do I need to memorize all this, Prandtl number, etc.? So I'm just going to bring down that table. I'll come back to this again, just bringing this down. You'll be able to see that your Prandtl number is also given over here. Okay, so you will have to memorize that Prandtl number. Mu over alpha. So the print is pretty small, so make a print out and then have a close look. Some students thought that this is letter A. It's not letter A, it's alpha. This letter over here is alpha. And alpha stands for thermal diffusivity. So normally what we need to do is to conduct a set of experiments with Reynolds number and Prandtl number in order to decide what is the Nusselt number. But I just want to spend this stage over here kind of to tell you physically what is Nusselt number. Nusselt number is H L over K. We know that's the formula for Nusselt number. Physically, Nusselt number given by symbol N and small letter u. It relates to the measure of convection and conduction in a flow where laminar flow is characterized by Nusselt number close to 1. And turbulent flow experiences more convection and is characterized by Nusselt number between 100 to 1000. That's because over here it relates to conduction, because thermal conductivity, and over here it relates to convection. So Nusselt number relates to the measure of convection and conduction in a fluid. So if you have Nusselt number that is close to 1, that means the flow is kind of like laminar. Just roughly. It's not used to decide that. Reynolds number is the one that's used to decide that. Just to let you see, because your Nusselt number is actually a function of Reynolds number and Prandtl number. So then, what is the meaning of Prandtl number? So Prandtl number, represented as P and small letter r, it relates the relative thickness of the hydrodynamic, or sometimes we call velocity field. It relates that to the thermal, or sometimes we call it temperature field, boundary And heat transfer governed by smaller Prandtl number would be dominated by thermal diffusion. And larger Prandtl number, what it means is it signifies momentum diffusivity. That's because your Prandtl number is actually nu over alpha. So the top part is your kinematic viscosity, and the bottom part is your thermal diffusivity. So this kind of like try to explain what is Nusselt number, trying to explain what is Prandtl number, and you could copy that now, have a look again. Right? Larger Prandtl number means that you have more kinematic viscosity side. Or your thermal diffusivity, is kind of like weaker if you have larger Prandtl number. So I'm going to upload the next set of notes tonight, because yesterday I received some updated information about that. So I'll put all the updated slide information in the portal so that you can download it for next week. I have one announcement. Because you are a mechanical design engineering course, so I was looking at an opportunity. Okay, I'll come back to that this slide again, but just very quickly. There is a competition out there. If you're interested to participate in designing things, right, please, after this class, come to me. There's a first prize, second and third prize. Right? Only if you want to participate, you can come to me, and then I'll guide you through how to do it.
Right, 你看一下。